Hello, excuse me. Hello, everyone. Welcome back to OpenFOAM. So in the last video, we are talking about potential foam and how we apply that to our pipe flow, a thin pipe flow problem. So I'm on my other computer now, and I want to work on this computer. So I tried to actually clone my GitHub repository in. Nevertheless, there was something called index-pack failed. So what does that mean? Well, it means probably the files are too big. So anyway, I have this. I looked online, searched online, see whether there's such a problem. And yes, indeed, this is a common problem for very big repositories. So well, what we can do is this. Say git config. You turn off the call compression. Okay. Do this, and then git clone. So this does a partial clone, depth 1, then the repository URL, which is this repository URL. So that will partially clone things in. All right. And then and I'll just put this inside the what do you call it? I'll put this inside the description. Yeah. So yeah. Now let's do an overview. So we have done incompressible laminar flow. Laminar flow using IcoFoam. So that's laminar for pipe flow. Alright, we have done potential flow as well. So there's potential foam. That's for initializing flow, the velocity field. And well, what we know is that not all our flows are in exactly a laminar shape. So this is not true of all flows. Sometimes the flow is turbulent. So we need to start to learn turbulent treatment. Right? And hopefully once we do the turbulent treatment, we can check out the flow profile, the difference between the velocity profile for the laminar and turbulent for the pipe case. And I want to introduce us to something called piezo foam, which is the turbulent equivalent of IcoFoam, to help us sort out this problem. And that's where we are headed. We want to head during our next few videos to do turbulent pipe flow. This is the most simple case. Alright, turbulent pipe flow. Yeah. So there are a number of problems that we kind of want to address before we finish. Before we start turbulent pipe flow proper. Firstly, we know that in our Snappy X mesh, we had some really rough edges around here. If you've been watching the last video, the meshing process has kind of left some things out. And we know the way to solve that is with a relatively high refinement level. Let's say a refinement level of 5 or 6. 5 to 6. A refinement level of 5 to 6 will make sure that there's no such thing on the surface. It will make sure it's very smooth. But the thing is, with a refinement level of 5 to 6, you realize that it takes a very long time. It's way too laggy for the computer to handle. Alright? It's too laggy for the computer to handle. And what we can do with that is, well, maybe before we start, we can use a very coarse. I'm going to use a coarse block mesh. Okay, so we want to use a coarse block mesh to start with the regeneration of this geometry to make it fine, and make it more refined. So that's step 1. Then step 2, probably we want to take a look at the so step 2 is to regenerate a laminar profile. Now this is for, of course, the sake of thoroughness, right? So I want to open a second window of Ubuntu because this one is running. Okay, this one's running, so let it download. So I want to open a second terminal of Ubuntu. Yeah, you can do such things. So that's a neat trick we can do. Of course, that's limited to the amount of computing power you have. So if we look at okay, I'll just briefly explain. I'll shift this to the top then. Yeah, if we do look at the piezofoam solver, all right. Piezofoam solver, we will have a laminar. There's a laminar solver. There's a RAS and there's LES. So what do all these mean? Okay, so we're gonna talk about that too. So let's take a look, see whether this thing is opened up. So CD foam tutorials, and I want to bring our attention to this piezofoam, which is the turbulent transition solver. So it's like icofoam, but for turbulence. So there are 3 modes you can operate piezofoam in. It's the laminar version, the Reynold's average Navier-Stokes version, or RAS. This should be Reynold's average simulation. That means Reynold's average usually means time averaged simulation, and then LES is the large eddy simulation. So these are some turbulence models. So we want to go through some background on that, right? So these are some turbulence models. Turbulence model. We want to go through some of that. And step 3, after that we want to look at step 3 to see what this we want to take a look at what this Reynolds average stress is. So some theoretical background. So this is some revision for those not too familiar. Then step 4, we want to run this thing, run piezofoam using something called K epsilon model. What is K epsilon? We'll tell you in a bit. So this is a K epsilon model. So this is where we are going for the next few videos. And of course, the last one, number 5, we want to compare laminar versus turbulent, which is in this case modeled using K epsilon model. This is about the simplest model we can find for turbulence. We can find velocity profile. So we want to use some post-processing tools in order to get this done. So this is where we are going for the plan tentatively for the next few videos. We want to redo our Snappy X Mesh thing. Hopefully that turns out well. We want to regenerate a laminar profile using piezofoam. And then we want to look into the theoretical background behind turbulence and study this thing called the K epsilon model and what other models and why what we are doing for turbulence. And then the piezofoam. which is we want to go and use PiezoFoam, the K epsilon model, to do K epsilon model. And then finally, we want to do some post-processing. So this is very important, post-processing. Okay, pardon my handwriting. You want to do some post-processing to, what do you call it? Get a good comparison. Okay, so let's see whether this GitHub is done. It is not done yet, so I'll probably have to fast forward. All right, a few minutes later, you realize that this is done, and it looks like it's a very big file, 700 megabytes, right? So 700 megabytes thereabout. The next thing we want to do, go into the new directory, this is, and get the rest of see the rest of the clone. And we want to fetch unshallow, and okay, it's going to run another process. I'm going to wait a while. Well, I mean, just a comment here. Since it's taking so long, perhaps in future we might not want to have our GitHub. Okay, let me go on GitHub. Perhaps we might not want to have our GitHub, copy all these time files down. We may want to have a clean version, or something with less time steps. If not, there's really just uploading, downloading process. It's gonna take very, very long, and that's not desirable at all. Okay, so that's just a note for future reference to myself, to all those who do things there. And you just run this unshallow step, and then we do a git pull to finish up. Okay, so it's gonna take a while. I'm gonna fast forward again, and hopefully after we do fast forward, we'll be able to see the files we need to have, so that we can check out our laminar flow profile, see how it is, see whether it matches the analytical solution pretty well, despite the deformities, the little imperfections inside the pipe. Yep. And okay, yeah, welcome back. So after fast forwarding, I tried this git fetch unshallow twice and the git pull to see if we can get our thing up and running. However, we have this thing called the index pack failed. A lot of fatal errors. Well, however, despite this problem, when we went to Snappy Pipe Potential Foam, we saw that all our files were there. And then we go to Snappy Pipe as well. All our files are there as well. So that made me wonder what this shallow clone was about, right? When you enter this command. Okay, so what is this shallow clone with depth of 1? Okay, it appears that shallow clone. Yeah, so according to this website in Perforce, it says that if you clone git, all right, if you clone git, I can read this. Every time we add a new version and clone it down, it means that every clone not only clones the file in the present version, but every revision of the file ever committed. Means every file in the previous versions as well. What do I mean? So let's extend this. I'm going to try and zoom in here. So we have git, and then we upload, let's say this is version 5, right? But on GitHub, there'll be version 4, version 3, version 2, version 1, for example. So when you clone, you're going to clone every single version. You're going to clone every single version into the computer. Now that caused an error for us. So there was this thing called the shallow clone with a depth of 1, which means it only clones the, well, either this one or this and this. In other words, it doesn't clone all the, it does not clone all the previous versions. So that's why when we put git, when we execute git pull, and it will say it's fetching origin, and it's already saying it's up to date. So this is what a shallow clone is like. It's not the full, let's say version 1 to version 5. It only copies maybe version 5 over. So that's a limited shallow clone. So this is very useful. So make sure you do a shallow clone if you're going to clone my repository down, because it's been updating over many kind of cycles. So again, let's do a paraview, and let's see whether, come on, paraview. Yep, I'm gonna get paraview online, and we want to see whether okay, paraview. And so now fast forwarding again, paraview opens up. Let's go to this. We'll try see the GitHub workspace, then pipeflow, and let's see. We want to see this, which is very important. And apply. All right, so we have our flow profile. Okay, and I'm just going to zoom straight to the last one. Okay, I'm going to rescale. And pretty much it, yeah, it should be about 2 here. But you know, you can see that this is the outlet, and the other side will be the inlet, directly at 0.0001. It probably needs a bit more time in order to finish it. So okay, it's supposed to be 2 on top. Let's see whether it's scaling properly. 0.0002. Okay, so I mean more or less it's there. All right, so there is this profile, a parabolic flow profile. Fastest in the center, at the side it's almost negligible speed, which is the classic laminar flow profile. And we see if we use a filter, slice filter, and we're going to use apply, and we're going to use the velocity. Yeah, we can see that the flow profile is as such, the center being the fastest, the side being the slowest. And if you look at the entrance region, we see the boundary layers forming, and then it gets closer to the, it gets faster in the center, slower at the side. Yeah, totally expected for laminar flow. Okay, so yeah, so in the next video, yeah, we have already seen what we have successfully cloned it to a new computer. So remember guys, if you're going to clone my repository down, use a shallow version of a clone. Alright, shallow version of a clone, so that you don't run into the same problem as I do. Where is the shallow version? Should be at the side. Yep, so git config, you do this, no compression, and clone with a depth of 1. Then it should be able to download the appropriate files into your computer. And in the next video, we will want to regenerate a snappy hex mesh. Alright. Yeah, we want to regenerate the snappy hex mesh. And yeah, in fact, maybe now I'll just want to delete all these 0 files, because you don't need them anymore. We've already seen the results in the past videos. So I'm going to remove all of this so they make the file smaller, and I'm going to upload to GitHub. So git status, so git commit, deleted early transition part. Okay, so yeah, that's all I have. I'm going to just quickly upload this onto GitHub, and I'll see you guys in the next video where we will start our redoing of the Snappy Hex Mesh, so that hopefully we don't have all these funny little things at the side. Right? So see you guys next time. Thanks for watching, and goodbye. Please leave a like or subscribe if you like this video and find it helpful.